So in this problem, we're asked to find the pressure at point A based on this manometer that we have that's extending from point A up to some gauge that we have over here at point B. Um, and so this is, pretty clearly a manometer problem, a fluid statics problem. Even though we have water flow in this channel over here, we're basically asked to assume, or we have to assume, that the liquid that's within our manometer from here to here is all in the fluid static condition. And so to start with, we'll list our assumptions, and here it's just going to be simply that we have static fluid in the manometer. And since we know that it's static fluid in the manometer, we're going to have pressure moving up as our position within the fluid goes down. And so in this example, we're going to solve this by working our way through the system and essentially just applying this rule over and over and over. Okay, so we're told that we know the pressure at B, right? It's just this 87 kilopascals, and we're going to try to find the pressure at A. And so the way that I like to look at this problem, or one way to look at this problem, is just simply to march our way from point A over to point B. And so we're going to say that the pressure at A, and now, right, because that's where we're going to start. And then we're going to move down 5 centimeters within the within water, right? This first fluid that we have in the intervening location. And so we'll call that plus the pressure that we get from A to C in water. All right, that's positive because we're moving down. Plus the pressure that we get from here, the pressure. Sorry, and I'm going to label these points. I'm going to label this point here as point C. I'm going to label this point here as point D, and we'll label this point here as point E. This is given as B, and this first point here is A. So the pressure at A plus the pressure from A to C in water, so it's kind of moving down through that section, plus the pressure from C to D, and that's within this fluid of mercury. And then now we're going to move from point D to E, so we're moving up within the fluid, so the pressure is going to go down. It's going to be minus this pressure that we get from D to E. This is also in mercury. And then again, we're going to have a loss of pressure as we move from E to B, so minus this pressure loss from E to B within oil. All of that is going to be equal to our pressure at B. All right, so if we take our pressure at A and we move all the way through the system, wind our way all the way through this manometer, for all of those different points, we should get right back to this pressure at B. Now remember, these are positive because these signs here are positive. We move down in the fluid, and these here are going to be negative because we're moving up in the fluid. Okay, so now we can start actually plugging this in. And so we're going to have PA plus rho water times G times 5 centimeters, right? Because that's the height of that fluid column. Plus, this is going to be rho Hg, right? So the density of mercury times G times 4 centimeters. Minus rho Hg times G times 11 centimeters minus, zoom out a little bit, rho oil times G times 6 centimeters is equal to our PB, which is given as 87 kPa. And there's, so let's see, so to solve this problem, actually to plug in these values, one way to think of this is to rewrite all of these densities in terms of specific gravities. And if we do that, we'll gather together these mercury terms into one term, and we'll end up with Pa plus rho water times G times 5 centimeters plus rho water times 13.6. This is the specific gravity of, um, of mercury. Times, and this is going to be 4 minus 11 centimeters, minus rho water times 0.9, a specific gravity of oil, times G. Sorry, this is dropped a G here in my mercury term. We'll put a G in there. Times G times 6 centimeters, 87 kPa. And now we can go ahead and evaluate all of this. And if we plug in, for example, a density, let's see, just to get an approximate answer, if we plug in a density of raw water of about 1,000 kilogram per meter cubed, and G, just ballpark here, we say G is about 10 meters per second squared. We can plug this all in and get PA is about equal to 96.5 kPa, which ends up pretty close to the answer that your book gets using these approximate values. And note here that if we just think about our significant digits, we were really just given everything to a single significant digit. So even this 3 is a little bit of overkill. And so I'd probably say a more appropriate way to express this answer is that PA is equal to 97 kPa. And there we go.